A quantum defeat of Maxwell's demon. Maxwell's demon is a thought experiment first imagined by James Clerk Maxwell in 1867. Maxwell suggested that a microscopic being, the demon, could violate the second law of thermodynamics. The second law demands that in a closed system, the overall level of disorder or entropy can only increase over time. In Maxwell's thought experiment, a closed box filled with gas is divided into two chambers, and the demon can sort fast-moving gas molecules into one chamber and slow-moving molecules into the other, decreasing the entropy of the gas. If this were possible, one could extract useful work from the gas without any energy input. One simplified version of the setup is the Szilard engine, which contains just a single gas molecule. By inserting a partition into the chamber, the demon traps the molecule on one side. He then determines which side it is on and replaces the partition with a piston connected to a weight. As it moves, the molecule pushes on the piston in weight, apparently extracting useful work from the system without any energy input. In her new paper, Dr. Ruth Kastner of the University of Maryland challenges the conventional understanding of how this paradox is resolved. Drawing from the principles of quantum mechanics, she argues that the system's entropy increases at the very moment the molecule's position is first measured by the demon. This contrasts with the conventional approach, which stems from a 1982 paper by Charles Bennett. He proposes that the demon gains the measurement result for free, but must eventually erase his memory to be ready for the next cycle of inserting the partition and detecting the particle's position. Bennett invoked Landauer's principle, which posits that erasure of information generates heat and increases entropy, so that the demon's need to erase his memory incurs an entropy cost. This matches the amount of work extracted from the engine, and at first glance, the second law is preserved. However, Kastner argues that the appeal to memory erasure is misplaced, and that the second law is actually preserved by the entropic cost of measurement. In fact, the demon does not gain the measurement result for free. According to the quantum uncertainty principle, any precise measurement of a molecule's position must increase its momentum uncertainty, and thus its entropy. Kastner argues that the erasure approach proposed by Bennett ignores the quantum uncertainty principle altogether, and as a result, it misses the thermodynamic consequences of trapping the molecule in one side or the other with the partition. Kastner shows that the mere act of trapping the molecule amounts to measuring its position, and this incurs an entropy cost, which exactly matches the amount that Bennett's theory attributes to the erasure of information. In conclusion, Kastner's analysis reframes the discussion of Maxwell's demon. Rather than being rescued through reference to erasure in information theory, the second law holds firm due to the fundamental laws of quantum mechanics. The demon doesn't fail at the end of its operation, but at the very start, through the simple act of measuring the molecule.